Hello everyone and welcome back to this channel. Today we are doing a short explanation on how linear regression models are assessed, what mathematical metrics, what evaluation metrics, what parameters are calculated to get to understand how well a regression model is performing in machine learning. So what are the list of evaluation metrics used for regression? So these are the parameters we will cover. It is a short explanation. These are the simple parameters. This is a part of a series of presentations which will cover more evaluation metrics used in different types of machine learning models. So this covers machine regression part. So as I just said, we are just covering the regression part. Now, for classification, there is a separate explanation. And as we progress through the machine learning models, which are unsupervised models and some other deep learning models, we will understand the metrics that are applied. Starting off with the first measure, that is the mean absolute error. And as the word suggests, it takes into consideration the absolute value of error. So the difference between this predictor line and the actual observations, these are these points, these differences could be negative or positive. So for the positive values or the negative value, we are just taking a measure of this distance. So it is a straightforward assessment of average magnitude of error. So we are taking average of absolute differences, of the sum of absolute differences. So what are the advantages and disadvantages? It is easy to understand and interpret because simply we are taking the same unit of output and input. We are not doing any mathematical operation on that, and so it is easier to interpret that there will be. So for example, if this is in meters, so the difference will also be the error term will also be expressed in meters or whatever unit that is being used and the dependent on the and the independent variable. Another advantage is it provides a linear measure of error, so it making it less sensitive to outliers. So if there is a huge outlier like here or here, so what we are doing is, because this outlier with having a negative sign may impact the calculation by a huge margin, we are just considering the positive values or the absolute values of these outliers also, which will give us an idea of a measure of what are the error terms. Irrespective of the sign will disrupt our calculations. And as I said, it is easier to understand and interpret because the error values are in same units. So one disadvantage is if you remember from your high school mathematics, the absolute whenever take a mod of a function, the graph looks something like this. So at this point, although it is giving a minima, but it is non-differentiable. So non-differentiable would mean the slope at this point cannot be defined. We cannot say the slope is this. It could be this, it could be this, it could be anywhere. It could range from anywhere. So this point is not differentiable. So for complex cases, when you are trying to optimize the value, when you're trying to find the minimum of this value, because at the end of the day, we minimize the cost functions. So if this is a cost function which we are trying to minimize to find the optimum values, where the minimum of this graph will lie, we will not be able to differentiate and arrive at the optimum value by minimizing this function. So you can remember from the linear regression explanation also, we were using a mean squared error terms where we were differentiating a quadratic equation to arrive at this point, and this would give us the optimum values of beta naught and beta 1, where we use the equation of simple we used a equation of line as beta naught plus beta 1 x is equal to y, where y was the dependent variable. So in this case, it cannot be differentiated. This cannot be used to get an optimum solution using differentiation. So another this it can while thus ignoring sign through absolute values was an advantage, it can be a disadvantage of signs also, because if we have large negative values or here's a cluster of large negative values, by taking the same sign of negative and positive values, this will be the fact that we have this line is not or this line, or we are trying to reach at a model which can consider the which is considering the outliers. We are not sure whether these outliers are of positive or negative sign through this method. So this is one disadvantage. So because of these disadvantages, we have another. So then we move to the mean squared error term to evaluate the regression performance. What does mean squared error does? Error terms, the squares of these terms are taken and average of these squares is taken. We use the sum of squares and then we average it out. Then we get the mean squared error. So there are certain advantages and disadvantages of using this MSE metric. So what is the advantage? It puts more emphasis on large errors due to squaring. So if there are large error terms, if we have error terms which are large, when the line is quite far away from the observed values, by squaring the large error terms, it is taking into consideration those large terms also. So the line will adapt accordingly. But it has its own flip side. If the error terms are too large, that means these values are outliers. So if we have outliers and we are squaring the outliers, this line will change drastically. The slope of this line will change drastically. So it is too sensitive to outliers. So this is an advantage and a flip side also. It all depends at the end of the day on the data. We need to check out how the data is and how is the behavior of this linear regression line according to the data, and then we take a call that which term is better describing and how to move forward on that model and what changes are required to be done in that model. So we take the root of mean squared error terms to get the RMSE, which is nothing but a standard deviation of residuals by taking the square root. And the advantages, as I said, it was it gave the measure was in the same unit as the target variable. It was same unit as y and x because we are taking the root. But again, taking the root may not be that advantageous because at the end of the day, we are losing a fair we are losing the idea of a measure of how big these error terms are by taking the under root. But again, since we are taking a square of error terms in the first place, the outliers will affected adversely. The outliers will affect hugely on the value of RMSE. So again, this is the flip side. This this advantage and disadvantage are two sides of the same coin because the advantages with large errors will be taken into account because of squaring, but again, outliers will cause the model to behave erratically because the slope will be uh, affected due to outliers too much, and it might not give us an optimum fit or a best fit line to make predictions. So after root mean square error, we come to R2 score. So this is the most commonly or the most commonly used measure to understand the performance of linear regression model, R square. And for complex, we also have something called adjusted R square, which we cover in the next slide. But let's understand R square first, which is the most basic and the most important measure used to understand the performance of linear regression models. So to start off, this is the formula. We will explain this formula using this graph. So how we'll do that? Let us take this point A. So on an XY axis, this is it. We have taken an example of monthly income and expense and how the expense move and the income also moves. So at this point A, let us have this. We have for all the observed values, we have taken an average value, which is y bar. This is the average value, average of all observed values, and this is our predictor line. This is the regression line. This is the best fit line, uh, which is noted by y hat. So this point A has a distance from the average value, and this entire distance is called as the total sum of squares, or the SST. This is the total distance, and this distance can be broken down into two portions. One is the explained variance, explained difference, and one is the unexplained difference. So the explained difference is the part between the average value and the predictor line. This part is the explained difference. This is the unexplained difference. Unexplained would mean the observed value lies somewhere here, and this is at a certain distance, say B, from the predictor line, and this was A. So this A, so this A is the explained difference, this is the unexplained. And these are also known by the name the sum of squared residuals, the sum of squared of error terms. So we are doing a sum of squared error terms, which is y minus y hat. This is the y hat. So y hat value will lie here, and y is here, the observed value. And this is the SSE part. And this is SSR part. This is y hat minus y bar. Y bar is this, which is the average of all observed values, and y hat is the predictor line. So when we take a difference and we take a sum of squares of this difference, we get this term SSR, and this is SST. So how do these two or these three measures, SST, SSE, and SSR, used to calculate the R square? So R square is calculated as 1 minus, this is y observed minus y hat, the predicted, that is SSE. And this is divided, the sum of squares of these values is divided by y minus y bar, which is the average value. So y is the observed value. So this is the total sum of squares, y minus y bar. This is the observed value A. So this is where A lies. This is the A observed value, and this is the y bar is the average. So this is the total sum of squares. So in denominator we have SST, and this is one. This is so this is y minus y hat, which is the B part. So this is B by B plus A. You can say that 1 minus this is B by B plus A in simple terms, not considering the squares per se. So now we have this measure R square, which is calculated as 1 minus this is that. So R square needs to be closest to 1. This ranges from 0 to 1. This measure ranges from 0 to 1. And we are looking at a metric which should be closest to 1 to give us a hint that this model is good. So in order to say that, okay, so the model which was achieved at a certain B naught, that is the coefficient, which was the intercept, and B1, which was the slope. So this line is governed by is identified by these two parameters, B naught and B1, and these B naught and B1 should be, this line should be explained in such a manner that the difference of these the error terms should be minimum, and for that to be minimum, this R square, this metric should be there, which should say so that there, for example, close to 1 is a value 9.96. So if a metric is there which tells us that this particular line explains 96% of the observed data, that on an average 96% of observed data is described by this line, and this is what R square is telling us. And how do we arrive at that? So for this to be 0.96, this should be minimum. This should be minimum. That means this should be 0.04. So for this to be minimum, we saw that this denominator part is B plus A, and above on the numerator is B. So the B part should be maximum in order to for this part to have a small value. So this B part should be minimum actually. So this part to be minimum, this part will be maximum. So these are two components out of the total, B and A. So if B is less, then A is more, and we want B to be less. We want this line to be as close as possible to the error terms. We want the B to be less. And when B part is less, which is nothing but y minus y hat, this part. So this numerator should be less. So what happens is R square will be closest to 1 because this part is closer to 0, because this part is small. We want this part to be small. And this is how we arrive at R square. And this is when we see that when R square, say for example, R square has a value of 0.96, we see that the model is quite good and 96% of the data is explained by the line. This is how R2 score is, or R square uh, term is explained. This is how R square is used to understand how good a model is. So coming on to adjusted R2 score or the adjusted R square. So why do we need adjusted R square? So in real life, in regression, there are more than just two or three parameters. It is not a two-dimensional or three-dimensional. It is a multi-dimensional space wherein the number of predictor variables is not just x. It's not just a y is equal to mx plus c or y is equal to beta naught plus beta 1 x or b naught plus b1 x. It is a combination of multiple independent variables which can be denoted by x1, x2, x3 and so on. So in real life, when parameters are added, we have a risk of overfitting, which is overfitting. The term has been explained in the previous explanation, the linear regression explanation, advanced linear regression explanation also. So in order to avoid overfitting, we need to have a parameter which is called adjusted R square, which will work in such a way that when more and more variables are being taken, are being considered to arrive at the this particular graph or the best fit line, when more and more predictor variables are taken, there should be some penalty imposed during that calculation so that not all the parameters are taken and the line does not overfit, because when line will overfit, it will not give us good results when some new data is given to that line to make some prediction. So in this slide, what we have done is we have taken a curved line instead of a straight line, because in real life scenarios, it might not be a simple linear regression. It could be a polynomial regression, or it could not, it's not definite, it's not like it will always follow a linear relationship. So this has been taken for the sake of that understanding. So just like in previous slide, this is broken down. The distance between the average value and the observed value is broken down into two parts: the explained and unexplained variation. The explained variation happens between the two lines of average and the predictor line or the model line, and this is the actual value. So so now coming back to adjusted R square, how does it work? How does it penalize the introduction of more and more parameters? So if you look at this formula carefully, there is a term called n minus 1 divided by n minus k minus 1. Now this n is the number of data points that are available, and k is the number of parameters that are there, which is what I was talking about, x1, x2, x3 and so on. So now what this formula is doing is it is bringing n and k face to face. So when k is increasing in when keeping n constant, n is the number of data points. So we have a certain fixed number of data points, but we are increasing the parameters that we are using in our model, which is k. When we increase that, this whole portion, this when k is increased, this will decrease. When this will decrease, this part will increase. So when this part will increase, so for example, the formula says, so when this part will increase, it will be higher than 1, because now naturally n minus 1 are common. K is an additional penalty that is happening in this fraction, and if k is say 5 or 6 or 7, it is getting subtracted from n minus 1 only in effect. So when it is getting subtracted from n minus 1, this part will become less and this fraction will become greater than 1. So for example, this fraction becomes say 5. 5 into 1 minus r square. So what has happened here is, if this was not 5, if this was 1 only, then this formula would be simply r square. So if there was no penalty, this formula will become r square. Now adjusted r square is accounting for the penalty, because the penalty is causing this 5 to come into the picture, causing this value greater than 1 to come into the picture. So when this 5 is subtracted, the final value will be r square. And how? Because 1 minus 5 minus 5, it's like 5r square minus 4. So this is what will happen when this term is introduced. So if this is if this value is lower than the initial r square value, we will get to know that this model is not getting better by incorporating more parameters. more parameters introduction would cause k to increase, and for if increase of k is leading to decrease in this value, or decrease in adjusted R square value. This is nothing but the adjusted R square in this case. If this is decreasing by introduction of higher Ks, then that introduction of that particular K or that particular parameter is not helping the cause of our model. So we are taking an example here. So for example, let n is equal to 100. There are three predictors and adjusted R square is calculated. We are putting the values here and we find that from 0.80 initial value of R square, the adjusted R square becomes 0.79. So this value is decreasing. So when this value is decreasing, we see that model is not getting better. So this is how adjusted R square by introduction of penalties is ensuring that our model accounts for higher number of parameters so that the model does not overfit the existing data and we get a good model which can predict the out of data, uh, can make predictions from new data also. So summarizing what we have learned here is these are the 5 metrics that have been covered. MSE is used when you want to penalize the large errors because it is at the end of the day squaring the error term, and when squaring happens, the penalization is higher. And MSE is used when we need a differentiable measure because we saw that the MAE, the absolute error, the graph is not differentiable. MSE is used for which gives us a differentiable graph for optimizing the best fit line to getting those parameter values of beta naught and beta 1. By way of differentiating, we got that value of beta naught and beta 1, which would give us the best fit model. And root mean square is again, we take a square root of MSE, and over MSE, it has an advantage that it has the same unit same unit of the target and the predictor variables. And in cases where the coefficient values are high or the unit interpretability is a requirement, we use RMSE instead of MSE. So coming down to R square value, we saw that higher the R square, it lies between 0 to 1. The higher value means it is the graph that we are obtaining, or the best fit line that we are, or the best fit graph that we are trying to arrive at is covering the large proportion of observed data is being covered by that line. This is what R square does. And adjusted R square, it is an improvement over R square where the number of parameters are high, and it adjusts for the number of predictors in the model by penalizing the introduction of additional parameters. So this is what adjusted R square does. So in the upcoming presentations, we will take up more evaluation parameters for classification, and then moving on with more and more machine learning as we move along with the more machine learning models, then more and more evaluation metrics shall be explained through separate presentations. So thank you for listening.